Hi, this is Rishwant, and I'm doing this presentation as part of assignment COT 5405. So I have been asked to find the longest common substring in linear time. So for this video, I'm going to construct a suffix tree using Ukkonen's algorithm. So with this suffix tree construction, I can find the longest common substring in linear time in time O of n. So basically, uh, so I'm going to create a suffix tree using Ukkonen's algorithm. So Ukkonen's algorithm basically creates a suffix tree in time O of n. So let's say if there is a string s of length n, so this Ukkonen's algorithm creates a uh, suffix tree in time big O of n. So this is the main purpose of Ukkonen's algorithm. So before jumping into creating a suffix tree, we have to learn three rules while constructing a suffix tree. So the rule number one is, if there is a new character in a string, add it to all the leaf nodes. So the rule number two states that if there is a new character that doesn't have a path from node, create a new leaf node for that particular character. So the rule three states that if the path that you want to see is already present, then don't do anything. So let me take a string S, for example, ABC, AT, ABC. So we have to create a suffix tree for this string. So basically, what is a suffix tree? Suffix tree is nothing but suffix. It can have more than two children at each node, so that each child of a node is unique. So let me take an example. Let's say this is the root, and we have three nodes, x, y, y, z, zx. So since the first character of every node is unique, so this is basically a suffix tree. For suppose uh, if I consider that y x at this particular node, so then it doesn't form a suffix tree. Okay, so we have to make sure first character of each path is unique, and using suffix tree we'll be able to get all the suffixes of a particular string. So there are many applications of suffix tree, especially in string algorithm fields and algorithm. So small example of this suffix tree for this is CATABC. So there are many suffixes for a particular string. Basically, there are n suffixes. Basically, there are n suffixes where n is the size of a string s. Uh, So let's discuss an efficient way to generate all the possible suffixes, and later on we'll be seeing how this suffix tree can be used for particular algorithms. And in this video, I'll be discussing about two algorithms. One is substring search, and another one is longest common substring. So basically, what substring search is, if the, for example, if there is a string of yeah, string AB. So let me consider one more suffix saying that BA. So I just want to find if this BA string is a substring of this suffix. So since this BA is present. So this is basically how substring search works. So let's come to longest common substring. So let's say there are two suffixes AB, and one more thing is BA. So we have to find the longest common substring. So the longest common substring in this is BAB. So after constructing a suffix tree, we'll later on find how we'll find the longest common substring using a suffix tree in linear time. So for both of these problems, we'll be using suffix tree, so that first we'll construct a suffix tree, and let's see how we do that. Yeah, coming to Ukkonen's algorithms. So basically there are 5 variables that we keep track to construct a suffix tree. So the 5 variables are remaining, active node, active edge, active length, and the end. So basically what this remaining says is, it says number of remaining suffixes that you still have to construct. So what this active node says is, currently basically it's currently a root node, which is the first node. So active edge is the current edge, and active length is the length where that particular character is at, and end says that end of a particular suffix which will be dynamically changed. So in this algorithm we don't use, so for example, let's take a string ABC ABC. So considering this string, so in this algorithm, Ukkonen's algorithm, we don't use characters in the paths. Instead, we use indices of the array. So indices of the array means I'll consider this as 0, 1, 2, 3, 4, 5, 6, 7. So we'll keep track using the indices of the array instead of the character. So initially we have the root node, and before constructing a suffix tree, and these are all the indices. These are all the indices which we are seeing. And so before starting this, let me tell you something about these algorithms. So in Ukkonen algorithm, there are n phases. In each phase, we'll be getting all possible suffixes of a particular index. So this n value is basically the length of the string S. So let's consider that a string S has n phases from 1, 2, 3 till n. So for each phase J, there will be 1 to J extensions for that particular phase. So for example, if we are at phase 3, so there will be extensions from 0, 1, 2, 3. So this is what we have to keep in mind. So we'll be performing n phases on all the strings. Once all the phases are done, we are done with generating the suffix tree. That automatically. So one more important point we have to note down is that there is a property in suffix tree that prefix of a suffix in a suffixes of a string cannot be same. Let's say S1 equal to XYZ ABXYZ, and S2 is XYZ. So here if you see that S2 is a prefix of the suffix S1. S2 is a prefix of suffix S1. So in this case, we'll be generating something called implicit suffix tree. So we don't want any implicit suffix trees. It causes a problem. So to overcome this, we will use a random symbol. So let me add the random symbol $ at the end of each suffix, so that this is how we avoid this implicit suffix tree problem. So if you see here, x, y, z, z is not a prefix of suffix s1, is not a prefix of suffix s1. So this is how we avoid the implicit suffix tree problem. So let us consider a string as a b c a d a b c dollar. So these are the 5 default variables which is declared at the starting before constructing a suffix tree. So initially we are at phase I, that means we are initially on the 0th phase. Now we are just left with root node. So as the active node, whenever we start a new phase, we'll be incrementing the remaining value to 1 and end value to, we'll increment the end value to 1, so which is 0. Once we have done this, we have a new character a, and we don't have any leaf nodes to the root, and we apply rule 1, which states that if we have a leaf node, add character to the end of each node. Since we don't have leaf node, we'll move to rule 2, which says that if we have a root node and a new character, then we just create it if we don't have path from root node. So there is something similar to rule 2, where active length is 0 and active node is root node. Then check if the character has the path from root node. Since we don't have this character a path from root node, we will just create an edge. So this is basically a rule 2 extension. Okay, so here yeah, so I'll be indicating this as 0 to n. So basically in Ukkonen's algorithm, it doesn't like write characters on the edges of a node. This, I am just writing this for our convenience. And what does this 0 end indicates that this character, this edge is 0th edge and ending with 0. So that means, so this is the only character that we have on this particular edge. Since we have created the leaf node, so we will decrement the remaining to 1. So let's decrement the remaining to 1. Decrement, so the remaining will be 0. Since the remaining is 0, we will move to the next phase. So that means now this phase is moved to I is 1, and since we have moved to new phase, we will increment the remaining by 1 and the end by 1. So yeah, so since since we moved to the phase I is 1, so let's come to rule 1. So as per the rule 1, we'll add b at the end of each node, and now we have added b, and let's come to rule 2, which states that if the active length is 0 and active node is root node, create a new leaf node. So now I have created b, which says 1 to end, which means 1 to end is 1 at this stage. So which means b is the only character at this edge. So since we have created a new leaf, we will decrement the remaining to 0. Okay, so since we have decremented, since the remaining is 0 now, we will move the ith phase I to the next phase, which is 2. So since we have moved to new phase, the remaining will be incremented to 1, and the end will be incremented to 1, which is 2. So now as per the rule 1, we will add C at the end of each node. And now we, as per the rule 2, since active length is 0 and active node is root, so we'll be adding one more new node, so which is C. So the notation will be 3 to end, which means 3 is a edge and end is a, okay, sorry, we have to increment the end by 1 since we have moved to new phase. So this C is 3 to 3. So yeah, since we have created a new leaf node, we will decrement the remaining from 1 by 1, which means 0, remaining will be 0. And since the remaining is 0, the new phase will be moved. I mean, we will be moving I to the next phase. So since we have moved to the next phase, we'll increment remaining by 1, as well as we will increment end by 1, so which will be 4. So now as per rule 1, we have to check if this, sorry, as per rule 1, we have to add a new character at the end of each node. Now as per the rule 2, we have to check if the character is already present. So A is already present after the root, so we'll move to rule 3. So rule number 3 is basically is, if you are searching for the character path that is already there, don't do anything. Instead, increase the active length by 1. So there is one more thing that we need to do when we come across rule 3: increment the phase, even though remaining is not 0. So in this case, as per rule 3, we will be moving to new phase even though remaining is not 1, and we are increasing the active length by 1. So now phase is moved, so that we will be incrementing the remaining as well as the end. So now we are at the phase I here. So as per rule 1, we'll be adding D at the end of each node. And now if we see this active node, active and active length, edge and active length play an important role to find exactly where we were currently at previous phase. So if you see here, active node is the root node here, and active edge is 0 and active length is 1, which means, so previously in the previous phase, the pointer is here. So now we have to check, as per the rule 2, we have to check if this D has a path after A. Since we don't have D after A and instead we have B, we will be creating a new node in such a way that, let me show you. A. So this will become 0 to 0. And then I'm creating a new node, B, C, A, D, which will be 1 to end. And I'll be creating a new leaf node, D, from A to D. So this will be 4 to end. So since we have created a new leaf node, we will decrement the remaining by 1. Okay. So if you see here, we cannot move to the next phase since remaining is not 0. Okay. So whenever we are stuck at a particular phase, the one thing that we have to keep in mind is we have to increment the edge by 1 and decrement the active length by 1. So in this case, so the active edge will be 1 and the active length will be 0. So if you see here, as per the rule 2, if we have active length is 0 and active node as root node, so we will be creating a leaf node from the root. So which means D, which is 4 to and. So since we have created a new node, so there is one thing that we have to see, that whenever we create a new node, there is something called suffix link. So suffix link is basically a link from one node to another node, one node to another node. So let's say in phase J, we created two nodes. One is X and another one is S of X. So S of X is another node which is generated after X. So there will be a path or link from X to SX such that we can directly jump from X to S of X. If S of X is not generated, and only if X is generated for that particular phase, then there will be a link from X to root. So in our case, X is nothing but node A and S of X is not yet generated. So in this case, as per suffix link, so we will be creating a suffix link from A to root, such that as per the suffix link, since we don't have S of X, we'll be creating a suffix link from X to root. That means from A to root. Yeah, since we have created the new leaf, we will be decrementing the remaining to 0. Since the remaining is 0, we'll be moving to the next phase. We'll be moving to the next phase where ith phase is at character A. Now, since we have moved to new phase, we'll be incrementing the remaining by 1 as well as end by 1. So as per rule 1, we'll be adding A at the end of each node. So as per rule 2, now if you see here, so coming to rule 2, we have to find if this A path is present from the active node root or not. So if you see here, the path to A is present. So we'll move to rule 3. So which states that if a path is already present, instead you increment the active length by 1. So in this case, since we are present at this edge, which is the 0th edge, the active edge will become 0 and the active node will be the root node. So as per rule 3, we'll increment the phase even though remaining is not 0. So in this case, the ith phase will be at this position, at this character B. So now as per rule 1, we'll be adding remaining as well as the edge. So in this case, end will be 6 and remaining will be 2. And as per rule 1, we'll be adding character B at the end of each node. Yeah, as per rule 2, now if we see, we are at this point. I mean, active node is root and active edge is 0 and active length is 1. That means we are at point A. Now we have to check if there is a character B after A. So if you see here, now we can find that B is after A. So that we'll jump to rule 3. So according to rule 3, since we have already found the path to B, so the active node for this particular edge, I mean the character where B is residing, the active node for this particular edge is A. So we'll change the active node to A, and the active edge is changed to 1. So we'll change the active edge to 1. So as per rule 3, since even though remaining is not 0, we can move the next phase even though remaining is not 0. So now I will be residing, phase will be at point C. So since we have moved to new phase, remaining will be incremented to 1 as well as end. So remaining will be 3 and will be 7, and we'll be adding C at the end of each node. Okay. So coming to rule 2, if you see active node is A and the active edge is 1 and the active length is 1, which means now the pointer stays here. So now we have to check if, sorry, now we have to check if this C is present after this B or not. And as we see, C is present after B. So now we move to rule 3. Since the path we are searching for is already present, we will increase the active length by 1, so which is 2, and then we will move to the next phase even though remaining is not 0. So now the next phase will be at 8, indices 8. So in here, yeah, since we have moved to the new phase, we'll increment the remaining will be incremented by 1, which is 4, and end will be incremented by 1, which is 8. So now we, as per the rule 1, we have to add dollar at the end of each node. So as per rule 2, now we are at the active node A and the active edge 1. We have to consider the length as 2. That means we are at the position C. So we have to check if the dollar is present after C or not. Since dollar is not present, we have to create a one more node. So let me construct it. Dollar A to end, and this one is, so A D A B C dollar. So 3 to end. Now I have created a new node B. So as per so we have, since we have created a new leaf, we'll be decrementing the remaining by 1, so which will be 3, and yeah, so the remaining is reduced, and if you see here, the now the active node is A. So as per the suffix link, we can make the active node as root node. So now the active node is changed to root node, and if you see the active edge 1 is here from the root, and the active length will be 2, so that means the pointer is here. So if you see here, is the dollar present after C? No. So again we have to do the same process. So we have to create a new node. We have to create a new node after C again. So this will be 1 to 2. 1 to 2, and I'll be creating a new node C. So 1 says, so BC A D A B C dollar. So AD. So this will be 3 to end, and now I'll be adding dollar, which will be 8 to end. So now we have created a new leaf node. Now we'll be decrementing the remaining by 1. Okay. So as we have seen, we have created two nodes in the same phase. So if so we can as I said previously, as per suffix link, if we consider this B node as X, this C will become S of X. So I am creating a link from B to C, and I'm creating a temporary link from C to root, because in future we don't know whether there might be any new nodes coming up, or we are not sure if the new nodes might come or not. So now uh, we will move to next thing. Now, yeah, so the remaining is not still 0. So as I previously said, whenever we are stuck at a particular phase, we have to increase the active edge by 1 and decrease the active length by 1. So now active edge will be 2 and the active length will be 1. So if we consider the active node is the root node, and the active edge is 2, which is this, and the active length is 1. So the pointer is here now. Now we have to check if the dollar is present after C or not. Since the dollar is not present, we have to repeat the same process again by creating a new node after C. So let me create that. So one thing is ADABC dollar, which will be 3 to end, and dollar, this will be 8 to end. So we have created a new node now, and I have created a new leaf node. Now we can decrease the sorry. So as per the rule 3, since we are stuck at the sorry, so the since we have created a new leaf, remaining will be decreased by 1, and then since we are stuck at the same phase, we'll be increasing the active edge by 1, which will be 3, and active will be decrementing the active length by 1, so which will be 0. So now uh, if now as per like these variables, we are currently at the active root, and we are at the active edge is 3. Since we don't have the active edge, we will since we don't have the active edge, we'll be creating a new leaf node from directly from the new root, which will be, yeah, dollar, which will be 8 to end. So since we have created the new leaf node, we'll decrement the remaining by 1. So now the remaining is 0. So if the remaining is 0, we'll move to the next phase. Since there are no new characters, so this is the end of the suffix tree. So basically for this particular string, this is the suffix tree this is the suffix tree that we have constructed for this particular string. Now we have completed constructing the suffix tree. Now let's check if the suffix tree we have constructed is correct or not by taking some suffixes. So let's see from here. So if you see here, let me take DABC dollar. So if you see DABC dollar is present, let me take one more suffix, ADABC dollar. So now ADABC dollar. So let me check BC dollar. So if you see BC dollar, BC and dollar. So I have taken three examples, three suffixes, and all these suffixes are present in the suffix tree. So which is satisfying. So as per my knowledge, this suffix tree is correct. So now by using Ukkonen's algorithm, we have constructed a suffix tree. Now let's see how this suffix tree helps us in some of the algorithms to find linear time. So one application is substring search. So I have taken an string S as an example, XAB, XAC dollar. So this is the suffix tree which will be created for this string. So for suppose let's consider a suffix pxac dollar. So and one and a substring bxa. Now we have to check if this bxa is present in this suffix tree or not. So if you see here, bxa is present here. So that means every substring is a prefix of the suffix. So every substring is a prefix of a suffix. So by using suffix tree, we can find the substring easily. So this is one application. And let me move to the second application, which is longest common substring. So I have taken two suffixes and I have added the dollar at the end of suffix 1 and the dollar at the end of hash at the end of suffix 2 to create a new string. Now I have created a generalized suffix tree for this string. So generalized in the sense, if you see the S12 here, this indicates that S1, either S1 or S2, like these two suffixes have in common. So S12 indicates that. If I have taken another examples, the suffix tree might be different. It might have only X1, S1 or S2. So since I have taken these two strings, CD, CD, DC, DC, the generalized suffix tree has come in this way. So if you see here, we can find the longest common substring by finding the common strings. So if you see here, the common string like S12 has all the common strings. So the path that it has is CDC or DCD. So if you see here, CDC or DCD is the longest common substring. So either CDC, sorry, S2 is DC. So either CDC is the longest common substring or DCD. So this is how we find the longest common substring using a suffix tree. So basically it takes O of n time in it takes in linear time, it takes O of n runtime complexity. This is this is the least possible time in which we can find the longest common substring. Basically, if we don't use the suffix trees, the longest common substring will be found in O of n square. So by using suffix trees, we found the time complexity of longest common substring for a particular string in a time O of n. So thank you, Professor, for giving me this opportunity. Thank you so much.